Good evening, everyone. Welcome back to our class. The topic for today is the repeated measures one-way ANOVA that I will guide you how to do it in R. Okay. The repeated ANOVA, this test is used for analyzing data where the variables or the subjects you're measuring more than one time. Okay. This test is also known or referred to as a within subject ANOVA or the ANOVA within repeated measures. I believe that you have come across this one time already, I think last week. The within subject here means that the same individual or the same subject are measured on the same outcome variables under different time points or after a different condition, okay? Or like under 3-time preparation for something. Okay. For an example, if you would like to test the capacity of 10 students over 3 times on a specific preparation for their final exam, for example, so you want to see if the first time of test, second time of test, and last time, the third time of test is different in terms of their performance, whether their performance improves or not. All right. All right. So today we're going to use a built-in data set on our library. Okay. Before loading the library, loading the data, we need to load some important data. So we need to load the library. Okay. So the first library is called tidyverse, which is crucial to do many things. Okay. So library tidyverse, okay, the lower one, okay. So you can run, all right. So here, down here, it is already installed, all right. You can run it again in order to check. And the second library is called rstart, okay, rstatics. So the rstatic here, if you don't have, you need to download, okay. You need to install by going to the lower right panel here, okay, install, and you type rstatics, okay, rstatics. Then click on here and install. But for this video, since I installed already, so I will not do it again, okay? I just load it, okay? For this library, it is used for the another function called ANOVA underscore test. And also we use to convert, okay, convert multi-variables to factor. Okay, to a factor variable. For instance, a nominal variable that you represented by numbers, so number 1, 2, 3, 4, 5, for instance, that represent a student. Then, if you do not convert to factor, this may be read as a numerical variable. All right. So in order to make it clear, we need to convert it to factors. All right. So loading the data, we have a different way to load from previous time, loading the data. Okay. So the data here, it is in the library Daradium. Okay, Daradium. Okay, so I type data. Okay, so the data here is called self-esteem. Okay, okay, self-esteem. Okay, built in the library package Daradium. Okay, Daradium. You can also install first the library Daradium here, and then you just load the data self-esteem like we did before. Okay, so I run it. Okay, and I have the data already here. Okay, so I want to see first 6 row or first several row. I just see like I just type head. Okay, so the data self-esteem here, and then it say 4. Okay, I say 4. You mean 4 rows. Okay, so here we see ID. Okay, on the lower left panel, ID. It means the ID of the students, and T1, T2, and T3 here. It is the variables. Okay, indicating the time of measure. Okay, so the time of measure of the self-esteem. If you want to know what a self-esteem is, okay, we can see the description by doing this code. Okay, self-esteem. Okay, esteem. Okay, then you can run. Okay, so self is okay, esteem. Okay, self-esteem. What was it? So self-esteem here. I think I write it correct. Okay. Okay. So self-esteem here. You can see here. Okay. We can click on it to see. So the self-esteem data, it is the self-esteem score data for the repeated measure ANOVA here, which consists of 12 individuals that enroll into successive short-term trials. Okay, so the first trial, and then the second trial, and then the third trials, in order to see whether the self-control, the self-awareness improve over time. All right, and as you see, ID here on the lower left panel, 1, 2, 3, 4 something. It is the ID of the individuals that they are tested. Okay, and T1, T2, and T3, all the corresponding value here, it is the score of the self-awareness. For example, okay, the individual number 1, the first trial, they got 4 5.01. The second trial, they got 5.18. And the third trial, he or she got 7.11, and so on, so forth. All right. Okay. We can also see on the left, upper right left here, cell esteem, we have 10 observation, okay, just 10. But in the data description is 12, but in the data set only 10, okay, and 4 variable, all right. So in order to make it easy for the function in the tidyverse and also in the R static to compute, to run the code, we need to convert, okay, we need to transform the data into a long format. Okay, here I say gather, okay, gather the data column T1, okay, the T2, T3 into long format, okay, and then convert, okay, the ID like you see above here, okay, the ID and the time variable into factor variable, okay. We can do by doing this code, okay. But like we discussed earlier, before doing other further coding, further execution or script, we need to name our dataset into a short form. Okay, so I name df equal self esteem. Okay, all right. So renaming, this is called renaming the data into short name. All right, and then we need to gather and convert the data by using this code. So df, okay, equal df, all right, with this sign, okay, percent, bigger, percent, all right, and then we gather, right, gather here. So the key is the time, the times that we test the student key, okay, or we can say the factors, how many time. So key, it is an argument, then we say time. So refer to T1, T2, and T3, for example. And value, we want to gather all the value according to time. So the time is score, we name it score, okay? Score taken from T1, T2, and T3, all right? So after gather this to a long format, we just close the function, okay? But we need another function, which is to convert. We say convert, okay, class factor. So what variable? We have ID, variable ID, and time, all right? So you can check here, okay, you can check here whether they are correct or not, okay. So we have this one, okay, and we have this one is complete, okay. So we can just run, all right. So now we have a long format of df here, okay. 10 trials, I mean 3 trials, each comprises 10 individual, all right. So 3 times, it means 30 variable of, 30 sample, okay, 30 sample, each of it has 10 sample representing 10 individual, and they consist of 3 variables. The first variable is ID 1, 2, 3 until 10, and then repeat again 1, 2, 3. It means each individual is tested for 3 times, all right? And then here represent the time, okay? Time 1, and then time 2, and here time 3, all right? Okay, coming back. All right, so now we can do some of the, let's say, what is it? The descriptive statistic. Doing, okay, make it bigger. Doing some descriptive stats. We can use the library tidyverse with it built-in function in order to see the descriptive statistic. You can also see using different, different score, I mean, different coding. But here we can say df, all right, and with the sign again, the percent and bigger and the percent, and then we say grouped by. Okay, so what is the like the factors that we want to group? Okay, ID factors, the variables, the group representing group. So it is time, all right, and then we have another sign to do the descriptive statistic, okay? Say get the summary, okay, summary stat. And what is the stat function, okay? You can see the built-in here, there are many, okay, full and fine number, mean and standard errors, extra. But first you need to see the variables. What variable? We want to see score, okay? Score, and the types of descriptive statistic that we want to use is the mean and standard deviation, okay? So you can run the code and you get here, all right? You get on the lower left panel here, T1, the variable name score. How many sample? 10. What is the mean? 3.14. What is the standard deviation? 0.55. And trial number 2, okay, trial number 3. Or you can use the following code, okay? Using what? using T apply that we practiced last time. You can say df, it is the x, so it is score, okay? And then the index by time, df by time. And then the function is summary, all right? So you get here, summary, okay? Okay, so you can get all of these. But here, we can get some of the descriptive statistic, including mean, okay, first quartile, median, means, third quartile, and max, but no standard deviation. You can use the apply again, and then you just change the function. It is SD. Then you can find, all right? So T1, 0.55, T2, 0.86, and T3, 1.14. Are they the same? You can see here. The above one, okay? They are more or less the same, right? Okay. All right, so this is the descriptive statistic that we want to check. For other things that we want to see, if that you want to see whether there is outlier. So in this tidyverse function, you can check many things. You can also search for your study. Okay, so here you can say df again here, then the sign, bigger sign, and then group by. Group by what? Okay, so group by means checking the outlier. Okay, df. Okay, group by. Group by, you have to state the variable that represent the factors, the time different, first trial, second trial, and third trial, right? Group by here. So what is it? It is time, all right? And then the sign again. And what you need to do here is the other function, built-in function called identify outlier. Okay, it is in the R static. Okay, and then what is the variable, quantitative variables that we want to see? The outlier, okay, in the DF. So it is score, right? And the results on the lower left here. Time, okay, ID, score, outlier, and extreme outlier. So only T1 and T2 that have outlier. So T1 is ID number 6 has an outlier score of 2.5. This is the low outlier. And T2 on the ID individual number 2 score 6.9. But it is not an extreme outlier. So it's okay. No extreme outlier. Okay. So we may assume the ANOVA. All right. For the ANOVA, whether it is independent ANOVA or repeated ANOVA, the condition that we can use the ANOVA is that if we are comparing the mean of 3 groups, every group's mean has to meet the normal distribution condition. In other words, each data from each group has to have the normal distribution. To check that, we can also use this function, okay, checking the normality of the data. Okay, 3 groups, okay, T1, T2. From the previous code, I think you still remember, right? We use the T apply, okay, the T apply, and then the variables that we want to check its distribution. Okay, so df score, all right, and the index is the grouping factor. It is what? df time, and function is what? Shapiro test. Okay, so you can see the result down here. All right, so T1 here, okay, the p-value of the Shapiro test is 0.8 something. T2 p-value is 0.1. T3 is 0.3. All 3 p-value are bigger than 0.05, meaning that the data, okay, the data are normally distributed. Every one of them has a normal distribution. Okay, with the R statics, we can also use the code built in that library to check the normality by saying df and then the sign, bigger sign, and percentage group by. Group by is again the grouping variables. It is time, all right. So within time, what do we want to do? It is called the test, the function Shapiro test on which variable it is for. Okay, then you can run. So here the score, Shapiro test score, in Shapiro score unused argument. So it's a bit different from the normal Shapiro. It is the written code. It is not Shapiro.test, it is Shapiro _ test, okay, within the R static library. Okay, you can see here, right? Here, the p-value, T1 0.8, T2 0.1, T3 0.3. They are more or less the same. Okay, you can run it again to check whether they are the same. Okay, here. Okay, so T3 0.38, and you can see here, T3 0.38, T2 0.117, the same, T1 0.886, Okay, so this round up to 59. They are the same. You can use either of them. All right. After checking the normality of the data, now we know that the ANOVA in this case, okay, repeated ANOVA, one-way repeated ANOVA is met. The condition is met. Then we can use the analysis or computation of the repeated ANOVA. So here, doing the one-way, okay, one-way repeated measures ANOVA. Okay, you can say ANOVA. Okay, and the same with the R static, we can use the built-in function in order to compute or to run the one-way repeated ANOVA. Okay, so you can say you can build a model. Okay, you can build a model like this. Okay, here. So I say M1. Okay, a model. Okay, model ANOVA model 1. You can say repeated measure R1. Okay, equal. The built-in function is called ANOVA underscore test in the R static function. And then you need what data. Okay, if you don't use the data, you can write df dollars. If you want to use the data, you can state data is df and comma dv. It means dependent variable is score. Okay, score, and then the grouping. Sorry, not the grouping. The ID. Okay, the ID is WID is called here is ID, and the grouping variable. The name to indicate it in the argument is within. Okay, within. Okay, within here is time. All right. So the function is built like that. Okay. So we have one open bracket and then one closed bracket. Then you can run. Okay. In order to get the result of this RM1, we can use the function get. Okay. ANOVA table here in the library or static. Okay. And inside this function is the name of our model, which is RM1. Okay. Then you can get the result on the lower left panel. In fact, they want to see if the time, different time. Okay, DF, we have 2, and DFD, DF distribution is 18, and the F statistic is 55.5, and the P value here, you can see, okay, the P value, what is it? It's very, very small, okay, compared to the critical P value that we assigned is 0.05 here. So here's very, very small. If we put a star, it's 3 star, okay? All right, so we have here very significant. So P, I say 3 star. Okay. So the overall model of the one-way repeated ANOVA is significant, is very significant. Okay. And so we have to do another test, say the post hoc test. So the post hoc test we use here is the pairwise t-test. So t-test, okay, t-test. All the t-tests are used for normally distributed data and ANOVA as well. That's why we use the pairwise t-test. You still remember the pairwise t-test that we use for the independent ANOVA? Okay, it is the same. It's just only different in the argument pair. If it is independent ANOVA, the pair is 4, which means they are independent. Okay, for in this case, it is repeated ANOVA, which means pair. And then we can say Wilcox, pairwise. Okay, pairwise t-test here. Okay, so you can see here the floating function in argument x, it means the variables that we are going to test and group, the grouping factors, the adjusted p-value, what you want to have the adjusted p-value. Okay, so x, our x is df score, and our grouping variables is df time, and then the p adjusted equal, can say the home. Okay, so home is less conservative. So if any significant difference detected, there will be a high chance of detecting significant when we do the pairwise. Okay, so our result here. Okay, so T1 to T2. Okay, it is 0.0001. Okay, and T1 to T2, I mean T3 is 2.6. T2 to T3, it is 5 multiplied by 10 powers minus 7. Okay, all of them are significant different. All right, or within the library or static, we can also do the pairwise t-test as well. Okay, let's say pairwise t-test RM1. Okay, so it is equal, okay, the f and the sign, and figure the function pairwise t-test here. Okay, pairwise t-test. Oh, I forgot with the pairwise here. Okay, the pairwise here. Okay, it means true. Okay, pair equal true. because it is repeated, then we have different p-value. Okay, 0.0015. Okay, this is 0.000006. I mean 01. Okay, and then 0.0015 or round up to. Okay. Another code that we can use here with the R start. Okay, with the R static. I mean, right? So t-test. Okay, pairwise t-test between what and what. Okay. So from our data df here, so we don't need to use df dollars again. We just type the argument here, score, okay, as a function of time, and the pair here, true or false. This must be true, okay, because it is repeated. It means pair true, okay. And p adjusted here, method here, we take the same as home, okay, home. All right, so we can run. So here there is something, okay, something wrong. It's called error unique default x, okay, one unique applied. Okay, so here can need to be true, okay, and then again here. So in the R static, it is not dot, it is underscore, okay, underscore, right? Okay, can run, and pairwise repeated model 1. What is the result? Okay, you have now the result. Okay, the y-axis or the dependent variables that we are going to do the comparison is y, means score. The variable name is score. T1 to T2. Okay, pairwise between T1 and T2. Both of them have 10 individuals. Okay, the statistic, T statistic is minus 4 points, blah, 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 and the p-value is here. Okay, the p-value, the unadjusted p-value, and the adjusted p-value is here. Okay, so the p-adjusted p-value is 2 power minus 3. Our former results from the above one. Okay, I run again to make it clear. Okay, whether they are the same or not. Okay, here 2. Okay, 2 power minus 3, which is equal to 0.002. Okay, so 2 here. Okay, power minus 3. All right, which means this value they round up here, the 0.0015. But for the T1 to T3 here, T1 to 3 here, the adjusted p-value, okay, 1 power minus 6, and the same as our result here, 1 power minus 6. All right, the same. T2 to T3, they are 2 powers minus 3, and the same with this one. Okay, it round 15 to 2, and therefore the p-adjusted value in the scientific notation is 2 power minus 3. All right, so they are more or less the same. The difference is just the built-in function. One in the base stat library of R. Another one is the library R statics that we use in the first row. Okay, the first few row here. All right, here. All right. Okay. So I think that's all for today. Oh, by the way, you may want to see the plot. Okay, doing the plot. Okay, so we can do the box plot. Right. Okay, box plot. Box plot here. The F score. Okay. It is the F grouping variable is time. All right, and you want to rename, okay, the Y lab equal what? It is the what is it? The improvement, okay, the awareness improvement, the self-control improvement, or we can say just self-control, okay, self-esteem or self-control awareness, self-control score, okay, self-control score, okay, and the X lab equal what? Testing time. How many times? How many trials? 3 trials. Okay. And color. Color, you can use 1 to 3 or 2 to 4. Okay, I think that is all. Oh no. What is that here? Time. How many times? Testing time. Testing X lab, Y lab, box plot. Why? It's just only 2. Score. Okay. Time. Okay. And X lab, Y lab, color 2, 3, 4. All right. What's wrong with this one? Okay. Or we can say just box plot. If there is a if it is more than, okay, that is more than 2, we can use this one. Okay, so let's see here. All right, you get it now. With just this figure, it is no doubt that T1 to T2 is different. T1 to T3 is different. T2 to T3 is also different, okay? Because they are significantly more than each other based on just our naked eye, okay? That's why the p-value of the pairwise test is very significant, all right? Okay, so I think that more or less all for us, okay? I hope you got the message, okay? You got the understanding of when you use the one-way repeated ANOVA, okay? And in what condition, and how to do the plot. And there are 2 different ways of doing that. Actually, it's not just only 2, there are more than 2 of the way. Okay, I think that's all for us, and that's all for me too. So see you later.